So in class we stopped around example 8, part C. If you take a look at part C, we're asked to evaluate f of 2. So there are two ways we can do this, either by looking at the graph or looking at the piecewise function. If you look at the graph, you can tell that the y value when f is equal to, or when x equals 2, the y value is 2. Okay, so I really just wanted to get to part D, when we're asked to discuss the continuity of f of x at x equals 2 and at x equals negative 2. Okay, so the first thing I want you to notice is that on the previous page we have a definition for continuity that says f of c is defined to the limit at that c value exists, and that part 1 and part 3 are the same thing. So taking a look at 8D, we're asked for the continuity, so we need to use this definition in this case. So taking a look, when x equals 2, do I satisfy these three conditions? Well, first of all, if you look at part C, we're given that the actual point is defined, so this works out. And then for part B, we actually have a limit, so that checks out number 2 for us. Now the last thing is that we have to make sure that these two values are the same, and which in this case, it is the same. So therefore, f of f at x equals 2 is continuous. Now, if you look at the other one, when x equals negative 2, well, first of all, right off the bat, we violate the second condition. The second condition meaning our limit has to exist. Our limit does not exist in this case, so therefore our function is not continuous at x equals 2. So let's write that. At negative 2, sorry. And I know you can tell by looking at the graph, but you should have this 3 set of conditions memorized as the definition of continuity. Okay, before I start on example 9, I just want you to think about something. So let's say I want to think about the limit as x goes to infinity. So as x goes to infinity for x, well, where does that go? Well, that would continue growing to infinity. Now let's change that up. If I take the limit as x approaches infinity of 1 over x, what happens? Well, let's just start with something small. So let's just use the table really quickly. So let's start off with x equals 10. Then my fraction is 1 over 10. If I go with 100, then my fraction is 1 over 100. So then let's just be a little drastic. 1 million as my x value, then that would leave me with 1 over a million as our y value. So taking a look at this, did you notice as my x's got bigger, then what happened to my y values? My y values got smaller. So small that as x goes to infinity, as this gets bigger, then that means this will go to 0. So the limit of 1 over x as x goes to infinity is equal to 0. Now I'm going to reverse this, okay? Let's say I take the limit of 1 over x as x goes to 0. So let's see what happens. Okay, let's just say I start with the y value or x value 1, then that would give me 1 over 1, which is just 1. Okay, then let's say I go with 1/2, so I'm getting closer to 0 on the number line. That would give me 1 over 1/2, which is really 2. Let's say I go with 1/3, well, that would be 1 over 1/3, which is the same thing as 3. So then if I continue on, getting closer to 0, so let's say 1 over 1 million, that would be 1 over 1 over 1 million, which is really 1 million. So you notice, as x gets smaller and smaller, going towards 0, so smaller, what happens to the denominator? Or sorry, not to the denominator, what happens to my y values? As x is getting smaller, then my y values are getting bigger. So where does this end up going? This will end up going to infinity. So the limit of 1 over x, as x goes to 0, will go to infinity. What's happening? Well, I know that I can't plug in 3 into this function. So thinking about limits, as x gets closer and closer to 3, where does our denominator go? Our denominator will get closer and closer to 0. As the denominator gets smaller, then that means our whole fraction gets bigger, so therefore this is equal to infinity. Or is it negative infinity? Oh, that's our question for right now. So how do we check which one it is? Well, something we might want to check is the limit from each side. So let's say I check the limit from the left, and I check the limit from the right. And in order to check our signs, one way that we can go about this is we just pick a number on the left side of 3 and on the right side of 3. So here's the thing. I know that either it goes to infinity or negative infinity. Now, I'm not going to make this hard on myself by picking 2.99999 or something. You can even pick something like just 2, because that's clearly on the left side of 3. So if I pick 2, that would give me 1 over 2 minus 3, which is a negative number. So therefore, for this one, I would get a negative infinity. Now, similar for the other case, if I pick f4, that gives me 1 over 4 minus 3, and that gives me a positive number, so therefore this will equal a positive infinity. So that means if I were to graph this or sketch this by hand, this would be where? Okay, so at 3 we have our vertical asymptote. And in particular, on the left side of 3, our graph will do something like this. And on the right side of 3, our graph will do something like this. And what I mean by this is this will go towards negative infinity, and this will go towards positive infinity. So going back to the big limit, what can we say? Well, since our left and right limits are not the same thing, that means our big limit does not exist. Okay, so that leads us to part B, where I ask for the limit as x goes to 3 of 1 over the quantity x minus 3 squared. Okay, so for this example, we're going to just kind of argue it out by logic like previously. I know as x goes to 3, this is going to be smaller. So if the denominator is getting smaller, then that means the whole fraction is getting bigger. So this will go to either positive or negative infinity. So now we need to prove or show which one it is. So I'm going to take the limit of both sides, and let's see what happens. So I want to pick the right sign now. So something that's left of 3 is 2. If I plug in 2 here, what do we get? We get, well, it doesn't matter, right? Because the bottom is squares, so this will always be positive. So if you play with the same logic here, if I plug in something, it doesn't even matter. If I square the denominator, it'll still be positive. So therefore, this whole thing will go to positive infinity on both sides. So therefore, our big limit goes to positive infinity. So our limit does exist for this example.